All right, so today we're going to talk about volcanic hazards in Latin America. You may see many volcanic eruptions that look like attractive places to go to. You'll see videos about volcanic eruptions in Iceland with lots of people enjoying the view, and ones where people are sailing right up to them on a boat in Hawaii with the lava pouring out. Those are the kinds of volcanic eruptions that people are attracted to. But there's another kind of volcanic eruption, and those are ones that you want to run away from as quickly and as far away from as possible. Pretty much everything we're going to talk about today in Latin America is in the second category. There are very few volcanic eruptions that people run towards. And we're going to talk about a couple of eruptions today where people wish they could run away, but they were not able to. And we're going to use these two eruptions as examples of what are called nuées ardentes, or pyroclastic flows. Nuée ardente is a French word. And another one is lahars. Lahars is an Indonesian word. And we're going to explore the wonderful world of deadly volcanic eruptions. So, just to remind you, Latin America, especially the western part, is in the circumpacific ring of fire, and the fire refers to the volcanoes. We'll talk about earthquake hazards, which are also related to this. The circumpacific ring of fire is reflecting the fact that you've got subduction zones underneath here. And these volcanoes of Latin America, they're all of the sort that we've called arc volcanoes. All right, so there are 382 Latin American volcanoes. There's no lack of volcanoes in Latin America. So this is a complicated diagram with many colors, and you can see volcanoes with past deformation. Deformation is an indication that things are happening under the volcano that potentially could lead to an eruption. But these black triangles show deformation, but they didn't erupt. And then there are volcanoes that did show deformation and did erupt. These are the red ones. And these include the ones all along the western side of Latin America. And in addition, the Galapagos. We talked about the Galapagos and the Lesser Antilles. And don't worry about the modus est or hotspots. That's basically what space is seeing on the ground in terms of temperatures. Holocene volcanoes with no unrest during the last Pleistocene glaciation. Few of those in yellow. Currently erupting in green, currently deforming and erupting in red, currently deforming in blue, and naturally, the national volcanic observatories are shown here as well. So there's a lot of volcanic activity going on because there's a lot of volcanoes and they're quite active in Latin America. Here's a nice view of a couple of them. This is a national park in Chile with a nice volcano there. And this is just to remind you what is the relationship between the subducting oceanic lithosphere and the volcanoes. These are the volcanoes of Latin America, these continental volcanic arcs, with the exception of the Galapagos, which are hotspot volcanoes, you may recall, and the Lesser Antilles, which are island arc volcanoes. But most of the ones that they're most concerned about in Latin America are these continental arc volcanoes. Let's watch a 9-minute video. Hope you enjoy it.
Plate tectonics is a theory that describes how the solid Earth operates. In this video, we will look at details of the two most important plate tectonic processes, the creation of new plates at oceanic spreading ridges and the destruction of plates in subduction zones. The Earth's outer surface is divided into a mosaic of rigid plates defined by a network of plate boundaries. The boundaries are the main sites of plate tectonic activities. There are three types of plate boundaries: divergent plate boundaries, where two plates move apart; convergent plate boundaries, where two plates move towards each other; and transform faults, where two plates slide past each other. Divergent plate boundaries are also called oceanic spreading centers and are where new plate material is continuously created. Convergent plate boundaries mark where one of the two converging plates sinks beneath the other plate in a subduction zone. Convergent plate boundaries are deeply submerged, and an oceanic trench marks where the downgoing plate bends down to begin its descent. We now look at what happens deep in the Earth beneath divergent and convergent boundaries. Geoscientists refer to Earth's plates as lithosphere. Lithosphere is a rigid shell of rock about 100 kilometers or 60 miles thick. It is composed of Earth's outermost compositional layers, the crust, and the uppermost mantle. Plate tectonics happens because lithosphere slides over deeper, warmer, and weaker mantle called asthenosphere. The origin of the force for this motion is the sinking of dense lithosphere in subduction zones. Let's look at lithosphere creation beneath a divergent plate boundary where new material for two plates is produced. About 50 kilometers under the oceanic spreading center, the asthenospheric mantle rises and begins to partially melt. Melting here occurs when rising hot asthenospheric mantle experiences lower and lower pressure. Melting by lowering pressure is called decompression melting. These melts, or magmas, separate from the remaining solid mantle and flow up towards the region of plate separation, concentrating beneath the ridge axis. Geoscientists refer to this as two-phase flow because two phases, one solid, the other liquid, move independently. Liquid magma flows up, while solid residual mantle flows sideways. Eventually, the magma pooled beneath the ridge axis erupts as lava. When this lava cools and solidifies, it becomes the volcanic rock known as basalt, which makes up Earth's oceanic crust. Older basaltic crust moves symmetrically to either side of the spreading axis to create space for the new crust. This is the plate tectonic process known as seafloor spreading. At the same time, under this new crust, asthenospheric mantle cools and is added to the base of the thickening lithospheric plate. The new plate slides slowly away from the ridge, and the top of the plate, which is basaltic seafloor, collects sediments that slowly sink in the ocean. Water infiltrates into the crust and incorporates itself into the structure of the crust's constituent minerals, hydrating the aging oceanic crust. Much of this hydration happens at the spreading ridges, where spectacular hydrothermal vents teeming with life are found. Sediments and hydrated oceanic crust will become important chemical players in subduction zones. As the oceanic lithosphere ages and moves away from the divergent plate boundary, it becomes colder, thicker, and denser. When oceanic lithosphere becomes denser than underlying asthenosphere, it becomes gravitationally unstable and wants to sink. Eventually, oceanic lithosphere does sink into the asthenosphere at a convergent plate boundary, in a subduction zone. Plate convergence can create enormous strain at the interface between the two plates, causing powerful earthquakes in a region known as a seismogenic zone. As the plate sinks deeper, it drags the overriding asthenosphere down with it, inducing asthenospheric counterflow that draws in more asthenosphere. At the same time, The sediments and hydrated crust of the downgoing plate are increasingly squeezed and heated as the plate descends, releasing the water acquired over millions of years on the seafloor. The released water and sediment melts rise from the subducting plate into the overlying asthenosphere and cause it to partially melt. This type of partial melting, induced by fluid, is called flux melting. The melt produced is also basaltic magma, as in the case at the oceanic ridges. But this magma contains much more water and water-dissolved chemical elements, which distinguishes it from magmas produced at ocean-spreading centers. The buoyant basaltic magma rises towards the surface. Some reaches the surface and erupts in volcanoes, but some magma stalls and ponds in the lower crust of the overriding plate. Ponded basaltic magma heats the crust and causes it to partially melt, forming secondary granite magma. At shallower levels in the crust, ponded basaltic magma can excavate one or more magma chambers, where the magma cools and fractionates, a process where mineral crystals freeze out of the liquid magma and sink to the bottom, changing the basaltic magma's composition towards granite. Basaltic and granitic magmas can mix in magma chambers to form a spectrum of intermediate magma types. Granitic magma has a low density and rises towards the surface in balloon-like masses called diapirs. Some magma diapirs stall before reaching the surface, where they cool and solidify to become plutons. Plutons can be exposed on Earth's surface where erosion cuts down into the crust. An example of exposed plutons is the granitic core of the Sierra Nevada of California. It is probable that the Earth's continents are mostly constructed of this type of material. The key plate tectonic processes just described, the upwelling of mantle beneath oceanic ridges and the sinking of cool lithosphere in subduction zones, is part of a convecting mantle system that dissipates heat from the Earth's interior. Sinking of lithosphere in subduction zones powers the plate tectonic machine and makes the plates move. These processes also regulate Earth's carbon and water cycle, are responsible for forming many ore deposits, and may be linked to the evolution of complex life. Among the planets and moons of our solar system, only Earth has plate tectonics. Perhaps there are other planets in other solar systems that have plate tectonics waiting to be discovered.
Okay, I hope you enjoyed that video. Now, if subduction is happening everywhere beneath Western Latin America, why are there some regions with no volcanoes? And we can see them, right? Here in Panama is one. Here in much of Peru is another. Here in this part of Argentina and Chile is another. So that's kind of puzzling. Why do we have subduction? You know, subduction is everywhere going off to the east here, but not all of the region above the subduction zone has volcanoes. Why? All right, so it's basically the fact that in some cases we have normal subducted slabs, like we see here on top, and the subducted slab goes down steeply, and there's room for hot mantle to get in here and be affected by all of the fluids and things that are coming off the subducted slab. And those, hot region generates melts, and those rise up and make volcanoes. Volcanoes are telling you where the regions in the mantle beneath it are melting. Where we have flat slabs, we don't have volcanoes because that hot mantle asthenosphere can't get in there, and so it can't be affected by the fluids. Instead, we have regions of increased seismic risk in these flat slab regions. So pick your poison. Do you want to be dealing with more volcanoes or more earthquakes? That will perhaps influence your choice of places to move to in Latin America. All right, so here are the flat slab segments that we mentioned. So there's one in Panama, big one in Peru, another one in central Chile and Argentina. And as we said, there are no arc volcanoes. So here we can see where the flat slab regions are. And I want to draw your attention to this one in Peru in particular. And in this region, we have a region where there are plateaus and ridges on the Nazca Plate that are being subducted. And these blue regions are hidden underground, and these are affecting the buoyancy and thus the dip of the slab. There's another one down here in Argentina and Chile. And just to give you an idea why there are some regions that have flat slab, it's because the slab's a little more buoyant and it's going to come in a little bit flatter. All right, so here we have the top 5 killer volcanic eruptions in the world. So this is only since 1500 AD. And this is basically, there's been about 300,000 people have died as a result of volcanic eruptions. And number 1 is Tambora, 1815 in Indonesia with almost 100,000 deaths, mainly due to starvation after the eruption. Krakatoa in Indonesia, 1883, 36,000 died, mostly as a result of a tsunami. Mount Pelée in Martinique, which we'll talk about more, in 1902, 29,000 died by basically getting baked in a pyroclastic flow. And Nevada del Ruiz in Colombia, 1985, 25,000 people were buried by a mud flow, a lahar. And then Unzen, 1792, 15,000. So 2 of the 5 most deadly eruptions that have happened in the world in the last several hundred years happened in Latin America. And we're going to talk about these 2 in particular. These 2 are particularly interesting, and we'll learn more about them. All right, here is a volcano in Ecuador, Cotopaxi. This is a really interesting volcano we're going to come back to because it's at the equator. And many people think there can't be any glaciers at the equator, but if you get high enough, you can get glaciers. So this one is almost 6,000 meters tall, and that's high enough for it to be covered in snow. And some of these high regions in near the equator are covered in snow and have glaciers. And we'll talk about that in another lecture. All right, so let's talk about the deadliest eruptions in Latin America. So Nevada del Ruiz in 1845 was one. Cotopaxi in 1877, a few hundred. Soufriere in 1902, 1,600. Mount Pelée in Martinique, which we've talked about as one of the world's biggest, most deadly, 29,000 in 1902. One in Guatemala, 1,500 or so. El Chichon in Mexico, more than 2,000. And Nevada del Ruiz, 1985, 25,000. We're going to talk about these 2 more in this lecture. All right, well, let's talk about Martinique in 1902. So now we're in the Caribbean region, and remind you, this is the Greater Antilles. There's no volcanoes in them. This is the Lesser Antilles, and there's lots of volcanoes in them. So now we're going over here. This is the Lesser Antilles. Venezuela's down here. Trinidad, Tobago. These are not volcanic islands. But as we go through this part, these are the volcanoes, the volcanic islands of an island arc. Goes on up to here. And Martinique is right here. All right, so these are the volcanoes. You can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 or so. And these are responding to the westward subduction of part of the Atlantic plate underneath the eastern margin of the Caribbean. Here you can see a cross-section of that. My favorite volcano in this group is Kikumjeni. That's actually a submarine volcano. All right, so let's go to Martinique. Everybody likes to go to a Caribbean island, and here we have Martinique. Martinique is not a very big island, so this is 10 kilometers. So this is, about the distance from Dallas to Fort Worth, maybe. And this is maybe the distance from UTD to SMU or so, something like that. This was colonized by France in 1635, and to this day the island remains a French possession. About 1,100 square kilometers, about 400,000 people live there, and the highest point on the island is Mount Pelée, up here in the north. This MR is Morne Rouge. Don't worry too much about it. But we're going to be talking a lot about St. Pierre. That's where the trouble was. Next slide. So this is St. Pierre before the eruption in 1902, looking at Mount Pelée off in the distance. A nice tropical town. Doesn't look too different today, you know. And this is what it photographed what it looked like before it was destroyed. This was the economic center of Martinique. Okay, so let's just talk about what happened before 1902, the disaster of 1902. So, as you may recall, fumaroles are often associated with volcanoes that have magma at depth. And in particular, the degassing magma will release a lot of sulfur. And that sulfur comes out in fumaroles. And these fumarole is an opening on or near a volcano, and hot sulfurous gases come out of it. And if you see an increase in fumarolic activity, this is often a sign that a volcano is waking up. Maybe a new batch of magma has arrived, and who knows what's going to happen. But as early as 13 years before the eruption, the fumaroles at the summit of Mount Pelée started to show renewed activity. All right, so that went along for a while. In February of 1902, people in St. Pierre started smelling a lot of sulfur. Like, that's a weird smell. Where's that coming from? Well, it must be the volcano, but they didn't take too much. So in April of 1902, things start to really pick up. On April 22nd, the telegraph cable between Martinique and Guadeloupe was broken. In April 24th, the first sign of magma coming close showed up when a column of black smoke rose from the crater, and only up to a height of 1,600 to 1,900 feet. It was like, oh, that's interesting. In April 25th, the village of Prêcheur was covered in ash, and by April 28th, there were strong rumblings were heard as the column of ash and material from Mount Pelée became higher. Definitely the volcano seemed to be waking up. All right, now in May of 1902 is when things really happened. So on the 2nd of May, there was abundant ash falls and rumblings. The black column rising from the volcano, you would see lightning going through it. And the first ash fall was reported on the city of St. Pierre, with a thin covering of ash on the whole island. On May 3rd, there was total darkness over the village of Prêcheur to the north. And many of the inhabitants left Prêcheur and to seek refuge in St. Pierre. On May 5th, one of the sides of the volcanic crater suddenly fell apart, and it gave way to a devastating mud flow that destroyed a sugar mill and killed 25 people. On May 6th, the telegraph cable between St. Pierre and St. Lucia was broken, and you start seeing signs of glowing over the volcano. Nobody was going up to the top of the volcano now because it was just too active. And by May 7th, there were houses collapsing and trees breaking under the weight of the ash. All right, so I want to give you a sense of what a pyroclastic eruption, a new AR dot, is like. And this is a volcanic eruption that happened last year in Japan. And these things are fun to watch if you're far enough away. So we'll just show you the first minute and a half of the video. I hope you enjoy it. All right, I hope you enjoyed that video. All right, so why didn't the people of St. Pierre evacuate? It would seem kind of like maybe it's time to take a vacation somewhere else. But the reality was, people, there's a lot of inertia. People are sometimes like, okay, this will pass, this too will pass. The reality was, there were no volcanologists on the island, and the residents only knew about the mild eruption of 1851 to 1852. Well, the governor, though, was aware that there were people getting concerned, so he appointed a volcano commission with the most qualified specialists on the island: doctors, pharmacists, science teacher. And the first meeting, well, the only meeting of the Volcano Commission was May 7th, the day before the city was destroyed. This is the first and only report of the St. Pierre Volcano Commission. And I'll read it to you. The commission responsible for the study of Mount Pelé's volcanic phenomena met yesterday evening, May 7th, under the chair of the governor. After a careful analysis of the facts, the commission declares that, first of all the phenomena which have occurred so far are normal and are commonly observed on all volcanoes around the world. Second, since the craters of the volcano are wide open, the expansion of the vapors will continue with no earthquakes or rocks projection, rocks being thrown out of it. Finally, according to the location of the craters and the position of the valleys leading to the city of St. Pierre is perfectly safe. Please go to sleep and quit worrying. Next slide. Now, some people maybe weren't so convinced by those reassurances, and there were some people that left between April and May 7th of 1902. But travel records for the early morning of May 8th show that there were more people traveling to St. Pierre than leaving the city. And the story of Captain Leboeuf of the Italian bark Orsolina suggests that some of the population of St. Pierre would have been saved if they had more knowledge about explosive volcanoes. The Italian captain was a native of Naples, and he was very familiar with the Vesuvius volcano, which destroyed Pompeii in AD 72. He saw what was going on around the volcano, and he hastily left the harbor St. Pierre on May 7th without his custom clearance, warning that if Vesuvius looked like Mount Pelée did, Naples would have been evacuated, because they actually have experienced that kind of violent volcanic eruption. All right, let's talk about the different types of volcanic eruption. I've mentioned that there's some, one classification would be the volcanoes you want to go visit when they're erupting and the volcanoes you don't want to go visit. But there's actually more gradations than that, and we're going to go through them very briefly so you understand what this eruption was. So the first type is called the Volcanian, and here's a photograph of Volcanian eruption. It erupts new lava fragments into the air, moderately explosive, throws out a lot of volcanic ash, and also what they call bread crust bombs and blocks. These are mostly andesitic and dacitic magmas. They're very viscous, so they kind of erupt explosively. But these are not serious, dangerous eruptions unless you're very close to them. Let's watch a 1-minute video of a Volcanian eruption. Hope you enjoy it. All right, so second type, slightly more violent than Volcanian, is the Strombolian. These Volcano and Stromboli are both Italian volcanoes. Strombolian eruptions are intermittent explosions and lava fountaining of basaltic lava from a single vent or crater, and there's volcanic gases that are released. Sometimes it's a rhythmic eruption, sometimes irregular. And again, the fragments consist of partially molten volcanic bombs that become rounded as they fly through the air. And this is a close view of Stromboli volcano erupting some of these molten lava fragments. So let's watch a 1-minute video about a Strombolian eruption. Hope you enjoyed that. Now, the next in the list of violence is the Plinian eruption. Now, you remember Pliny was observed the AD 79 eruption of Vesuvius, and in fact, he was killed, and we have named this kind of style of eruption after him. Plinian eruptions are very explosive. They form enormous dark columns of tephron gas that rise high into the stratosphere, maybe more than 11 kilometers or 7 miles. Such eruptions, like we said, are named for Pliny. And so a lot of ash and tephra falls from the sky. This is a photograph of a Plinian eruption of Mount Spur in Alaska, and which sent the eruption column 18 kilometers into the sky. Okay, now the 1980 eruption of Mount St. Helens was also a Plinian eruption. So let's watch this one. All right, hope you enjoyed those videos and have a better sense of what Volcanian, Strombolian, and Plinian eruptions are like. So these things all put out tephra, which is kind of a funny word, but it's basically volcanic ash and fragments of different size. You know, there's fine tephra, volcanic ash, and then there's coarser material. It's a very wide range of material. It can be large, dense blocks and bombs, and smaller fragments, scoria, pumice, and ash. All right, now let's talk about a pyroclastic flow. So pyro obviously means fire, hot. Clastic means broken. We talk about clastic rocks, clastic sedimentary rocks. These are obviously not sedimentary rocks, although in a way they are because they're being deposited by gravity like sedimentary rocks. And the difference is the temperature is so great. So a pyroclastic flow is a ground-hugging avalanche of hot ash, pumice, rock fragments, and volcanic gas that rushes down the side of a mountain as fast as 100 kilometers per hour or more. So you're not going to outrun one of these. Temperatures can reach up to 500 degrees centigrade, more than enough to burn wood. And then once the pyroclastic flow stops, it could retain enough heat so that the ash and pumice and rock fragments may weld together, actually because of this intense heat and the overlying weight of the material. So these pyroclastic flows are also called nuées ardentes, glowing clouds. Right? Nuée is French for cloud, ardent is glowing. And they are associated with Plinian eruptions. And so this is a photograph from some distance away of a 1984 eruption of a volcano in the Philippines. And so you can see two things happening. Number one is this column of ash, dark, rising up, and the other one is this dense material that's making an avalanche flowing down the mountain. They happen together. All right, so here we have another view. This is, you can see the column that's rising of buoyant material and the pyroclastic flow that's sweeping down the sides of the volcano. Fortunately, there were no casualties from the eruption because more than 73,000 people were evacuated because of the Philippine Institute of Volcanology and Seismology said, I think we'd better do this. Philippines have a lot of volcanoes. They're well familiar what to do in a situation like this. All right, and then here is Colima, a nuée ardente or pyroclastic flow that happened in 1998. And this pyroclastic flow or nuée reached out to almost 5 kilometers from the summit. So they can go quite a ways. And you notice that they affect one direction, which you don't know which direction they're going to flow, but once it happens, you go, oh, gee, I should have been on the other side of the volcano. All right, so with that background, let's come back to Pele. So on May 8th, around 3 in the morning, everybody's sound asleep, mud flows started destroying houses in Grand Rivière, Macuba, and Basse Pointe on the north side. And not too long after that, a nuée ardente came out of the volcano and just wiped out St. Pierre. It devastated, a huge area, killing all members of the Volcano Commission. Only 2 people were actually inside the city who survived the blast, Superius and Leon Compere. So many others who were on the boats anchored in the harbor or were caught around St. Pierre were caught in the blast and killed. The only people who in the path of the blast were sheltered inside a building, a jail cell, or a boat where we had some protection from the intense heat of the nuée. All right, so here's what St. Pierre looked like before the eruption, and here's what it looked like afterwards. There's not much there. Okay, Superius the survivor is the interesting story. So I'll read it to you. Superius said that the cell he occupied in the St. Pierre prison was an underground dungeon which had no other window besides a grated aperture in the upper part of the door. On the morning of May 8th, while he was waiting for breakfast, it suddenly grew very dark, and almost immediately afterward, hot air mixed with fine ashes came through the door grating and burned him. He rushed and jumped in agony around the cell and cried for help, but there was no answer. He heard no noise, saw no fire, and smelled nothing except what he thought was his own body burning. The intense heat lasted only a moment, and during that time he breathed as little as possible. There was no smoke in the cell, and the hot air came through the door grating without any noticeable rush or blast. He had on, at the time, a hat, shirt, and trousers, but no shoes. His clothes did not take fire, but his back was very severely burnt under his skin. Now, the good news for Superius was he got a contract to show his burns in the Barnum and Bailey American Circus. So, there's a silver lining to every misfortune, hopefully. This is his cell. You can see it's a pretty good place to be protected from a pyroclastic flow, except for these openings. All right, now there are some other witness accounts of the May 8th eruption. On the edges of the pyroclastic flow, the heat wasn't high enough and the blast wasn't strong enough to kill instantly or to cause heavy damage. And so this is the account of Mr. Lasserre and Mr. Simonet traveling from St. Pierre to Morne Rouge on a mule-drawn carriage. So the pyroclastic flow came down this valley, and they were going up this ridge, so they had a bit of a chance. All right, this is their account. They saw the black cloud from the volcano coming just as they began the ascent of the Grand Woody, up to where they were headed. They lashed their mules into a gallop with the hope of escaping it, but the eastern edge of it caught them about 60 feet from the top of the hill. It approached with a roar, struck them like a mighty wind, overturned and wrecked their carriage, setting their mules free, and then swept across the summit of the Grand Woody, leaving them stunned, burned, and half dead in the shattered vehicle. They saw no flame or fire, did not notice anything like a suffocating gas, and smelled nothing except what they described as the odor of smoke from a lava, probably sulfur. Both felt the intense heat of the blast as it swept over them, but Mr. Lasserre did not realize that he was seriously burned until he crawled out of the wrecked carriage. Darkness came quickly afterwards, but they succeeded in getting into a small, deserted house where they waited until it became light enough so they could walk to Morne Rouge. Their clothing showed no signs of injury from the heat, but their backs were badly burned or scalded. The skin peeled off their hands so that it hung from them in strips. And when they arrived at Morne Rouge, their shoes had to be cut from their burned and swollen feet. So they were lucky. Now, a little bit later that year, another Nuit Ardente happened. This is a photograph of it. It gives you a feel for what it was like. All right, so just to wrap it up, on May 20th, a new paroxysm through a dense ash cloud, new violent eruptions late in May, more eruptions in June, and the activity ended in 1905. All right, this is St. Pierre today. So shortly after the eruption, of course, St. Pierre was completely abandoned, but slowly the families were drawn to the ruins by the cheap price of land and the desire to rebuild the city. The first building to be constructed among the ruins was a hotel, mostly thanks to tourism, which developed after the disaster. And there's about 6,000 people living in St. Pierre. Now, this story gets repeated a lot. We know this is a dangerous place to live, which means you can buy land more cheaply there than a place that might be safer. And so you take the risk or you don't take the risk. And we see this a lot. People know something about risks of living in Los Angeles or San Francisco because of the earthquakes. In Latin America, many people live near volcanoes and hope that when it erupts violently, they will not be around. But these things do happen. We'll give you another example. All right, let's go from Mount Pelée, which was the worst eruption, deadliest eruption, to Nevada del Ruiz, which was almost as bad and more recent, but a very different way of killing. So where is Nevada del Ruiz? It's up here in Colombia, northernmost volcano in the Andes, in the northern volcanic zone. And there it is, not too far from the capital, Bogota. It's the highest Colombian volcano with historical activity, 5,400 meters. The volcano is the second highest active volcano in the Western Hemisphere. It's a big volcano. So, big, tall volcanoes get covered with ice. And Nevada del Ruiz, even though it's very close to the equator, has a summit covered with 25 square kilometers of snow and ice. And the chronology of the eruption that we're going to talk about started in November of 1984, when the volcano started showing signs of unrest, earthquakes, more fumarolic activity from the summit crater, small explosions. People knew something was happening. Let's just talk a little bit while we're here in Colombia. Let's talk about Colombia. It's about a little over 1 million square kilometers, 50 million people, and the per capita GDP is $6,700 per year. Colombian geography is almost worse the course in itself. There are 3 mountain ranges lined up here. There's one in the west, and then there's one in the center, and then there's one in the east. And these are naturally called the Cordillera Occidental, Cordillera Central, Cordillera Oriental. And then this eastern part of Colombia is basically the headwaters providing tributaries to the Amazon River and the Orinoco. So very interesting scenic geology. So let's talk about a lahar. What is a lahar? Lahar is an Indonesian word for a rapidly flowing mixture of rock, debris, and water that originates on the slopes of a volcano. They're also sometimes called volcanic mud flows or debris flows. They form chiefly from rapid melting of snow and ice by lava, by heating by lavas, intense rainfall on loose volcanic rock deposits, or maybe the breakout of a lake that was dammed by volcanic deposits. Anything that puts a lot of water in motion down the side of a volcano. So volcanoes that are covered with ice and snow are particularly dangerous because a small eruption can melt a tremendous amount of ice and produce great lahars. Now, Martinique 1902 was bad enough, but at least it didn't have any ice on its summit, so you were not going to get drowned. You were not going to get you might get baked to death, but you wouldn't get drowned. But these big, tall volcanoes, a much smaller eruption can melt a lot of ice and water. So let's watch a 1.5 minute video on lahars. Hope you enjoy it. All right, let's go back to Nevada del Ruiz. And so here we're looking at it. Look, very impressive mountain. So prior to November 13th, 1985, which is when the problem happened, there were many earthquakes, steam eruptions for almost a year before the eruption. And it kept people very nervous because lahars had killed 1,000 people in 1845. And there are many more people living in the area since then. And a scientific commission and some journalists visited the crater in late February. By July, there were seismographs were obtained from several countries to monitor the earthquakes. A lot of these volcanoes, they're not equipped with modern equipment to monitor seismicity, which is telling you can monitor these earthquakes and see where the magma is moving. There was money from the UN to help map the area and where's the greatest risk. They finished this in October, more than a month before the eruption, but only 10 copies were distributed. Based on the report, the National Bureau declared that a moderate eruption would produce a 100% probability of mud flows with great danger for the city of Armero, Ambalina, and the lower part of the river Chinchina. We'll see more about where these are. But the government officials dismissed the report as too alarming, and authorities did not want to evacuate people until they were assured that it was necessary. This is always a challenge. When do you call an evacuation? Because we see this in the United States when hurricanes are coming. Please evacuate, and a lot of people don't. good things happen, bad things happen. Anyway, continuous tremors began beneath the volcano on November 10th. And so there was a scientific visit to the volcano in November 12th, but they saw nothing to suggest imminent danger, and they did not recommend an evacuation. So, the eruption of November 13th, 1985, there was an explosive eruption at 9 at night, and this generated an eruption column and sent pyroclastic flows across the volcano's broad ice-covered summit. Within minutes, pumice and ash began to fall to the northeast, along with heavy rain. The crater was enlarged slightly by the eruption, and the summit area was quickly covered with pyroclastic flow deposits as thick as 8 meters. That's pretty thick. And then there was a steam explosion, and the pyroclastic flow deposits in this picture are partly covered with fresh snow here, but that's the summit area. All right, so this was the hazard zone that people knew about, talked about, realized here's the volcano here. And then the hazard map zone, we've got high lava flow potential, which is just in the summit region. And there's a moderate hazard from lava flows, a little bit farther down the volcano, but nobody's living there. Then we have the pyroclastic flow hazard, like they had on Martinique, which extends farther down these canyons. And then we have places that are affected by the mud flow. And these mud flow areas that were affected are all of these river valleys, the Guali River, I can't read that one, Languanias River, and this is the city of Armero that was wiped out by the lahar. So these are the volcanic eruption and the pyroclastic flows even don't flow as far as the lahars do. All right, so on November 13th, the eruption stimulated the lahars. So that we talked about that initial blast at 3 in the morning and 3 in the afternoon. 2 hours later, there were pumice fragments and ash in Armero. But the citizens were reassured by radio messages from the mayor, from a local priest. Nevertheless, the Red Cross ordered the town to be evacuated at 7 at night. But shortly after the evacuation order, the ash stopped falling and the evacuation was called off. At about 9 at night, the hot tephra began to erupt from the summit crater and began to melt the summit ice cap. But there was a storm obscuring the summit region, and it's also basically nighttime. But that meltwater mixed with the erupting pyroclastic fragments to generate some hot lahars. And one lahar flowed down west down the river Cauca, killing 1,900 people. Others followed the paths of the 1595 and 1845 mud flows, traveling at 50 kilometers per hour. The largest of these burst through a dam on the river Lagunias and reached Armero 2 hours after the eruption began. Most of the town was swept away or buried in a few minutes, killing 3/4 of the people. So, what happened was, here in the headwaters of the Azufrado River, these hot lava fragments of the pyroclastic flows mixed with the ice and snow, melting about 10% of the ice cover almost instantly, and then began to flow down the channel, and it cut channels 100 meters wide and 2 to 4 meters deep, cut into the ice cap. And then all of this stuff just kept going down the mountain. And it took big chunks. In one of these rivers, scientists found a piece of ice 2 meters across that was 3 kilometers, that would be about there, from the crater. In the Guali River, just to the north, the same thing, pumice and meltwater produced flowed into these gullies and channels, and these things would erode, and so you'd add more and more material to the mud flow. And there were several places that it went down the Guali River. But here's an example of what it looked like after the mud flow had gone. You can see this is a densely forested region, but where the lahar flowed, it basically wiped out the trees. And so this is sort of showing you how wide the mud flow was and how tall it was. Some of them were times were as thick as 50 meters thick, flowing at 50 kilometers an hour. All right, this is the Gwali River, and so here you see the region affected by the lahar. And these people were fortunately up on kind of a ridge, but it must have been terrifying to see the lahar passing by them. They reported that the noise created by the lahars made their houses and the ground shake, and their conversation, even by shouting, was impossible. So that was a pretty high energy event. This is what was left of the former site of the town of Armero. You can see it looks like a region of sedimentation. And yes, there have been a lot of sediments deposited here very quickly, very thickly, and at the bottom of these deposits are the houses of the people. 3/4 of the Armero's 28,700 people died. Another view, some partial remains of houses. Some of these people very likely survived. And the closer they were to the river, the less likely. All right. So the accounts from survivors indicate that Armero was inundated with several pulses of flowing material, or lahars. The first arrived at 11:25 p.m. and consisted of a flood of cold water that overflowed the Lagunitas Channel and flowed into downtown Armero. It was only a few centimeters deep in town, but this was water that was from a lake just upstream that had been displaced when the lahars flowed into the upper portions of the reservoir, pushing the water down. The second pulse was the main part of the lahar that arrived 10 minutes later. This was the largest pulse, and in 10 to 20 minutes destroyed most of the buildings and killed most of the people. And this flow depth was 2 to 5 meters. The third pulse arrived at 11:50 with about velocity of about half that of the second one. And in the next hour or so, a series of smaller pulses were experienced. And these pulses, some people were stuck in the mud, and these pulses would lift them a little bit and push them a few meters ahead. And the last one struck Armero at 1 in the morning the next day. So it was like an hour and a half of pure hell. All right, so what did we learn from Nevada del Ruiz? For the generation of lahars on ice and snow-covered volcanoes, there's a lot we can learn from this. And it's useful for scientists, emergency response professionals, and communities located downstream of such volcanoes. First of all, catastrophic lahars can be generated on ice and snow-covered volcanoes by relatively small eruptions, something that would not cause a problem if it's on something with a lot of ice and snow can cause a big problem. I mean, the eruption of Nevada del Ruiz was not particularly intense. It was nothing like what happened on Martinique, but it killed almost as many people. The surface area of snow on an ice cap can be more important than the total ice volume when you're considering lahar potential, because it's just that upper surface that's going to be affected. Just putting hot rock debris on snow is not enough to generate lahars. They have to be somehow mechanically mixed together in order to really rapidly heat the ice. Fourth, lahars can significantly increase their volumes by entraining water and eroded sediment that they pick up on the way from their source down to where they're ultimately deposited. And finally, valley-confined lahars like those that flowed off of Nevada del Ruiz can maintain high velocities and have catastrophic impacts as far as 100 kilometers downstream. That's a long distance. Now, let's just close this by bringing it home a little bit to Mount Rainier. Mount Rainier is one of the most beautiful volcanoes in the United States, up in Washington. Seattle's well to the north of it. Mount Rainier is about here. But you can see Mount Rainier very nicely from Seattle on a clear day. Here's Puget Sound and Olympia and Tacoma. And this is Interstate 5. People travel north and south in there a lot. But it's potentially the most dangerous of all of the volcanoes in the Cascades in the Pacific Northwest. It rises 3 kilometers above several river valleys, and it is covered by snow and ice that is equal in volume to all of the snow and ice on all of the other Cascade Range volcanoes. And that's because it's so far north, it's so tall, and there's a lot of rain in Washington, and snow when you get to higher elevations. We know that there have been lahars that have come off of Mount Rainier. The most recent one happened about 500 years ago and swept more than 50 kilometers down the Puyallup River, I'll have to find out where that is, and buried the valley near a town of Orting, 3 to 5 meters thick. So, here we've got Mount Rainier National Park. I highly recommend, if you're ever up in that area, you take a look at it. Here's the town of Orting. It was buried by a lahar 3 to 5 meters thick 500 years ago. And look at all of these other towns. You wonder, do they know what happened there? How do they teach about the situation? How do the real estate agents discuss the situation with people that are flocking to Washington to enjoy its scenic outdoors? And what do they tell them about the risks? It would be interesting to know. I don't. I hope you enjoyed this lecture. Next thing that's going to happen is the midterm, and the next lecture will be on El Nino. See you then.